So hi everyone and welcome to our weekly AATRN seminar. The speaker today is Elchesen, and he will tell us about Möbius cohomology as a derived functor.
Okay, yeah, thank you for the introduction and thank you for the invitation to speak. Um, so yeah, I'm going to talk about Möbius cohomology. And as the title says, we're going to introduce it as a derived functor. But the idea is that this is a categorification of Möbius inversion. Um, so this is joint with my postdoc mentor at CSU, Amit Patel. Um, and really, so this is kind of an extension of work that he did with Primo Skraba, where they did Möbius homology. So we're extending this, we're adding the co in front of it, but then we're also going to extend this in a few different ways as well. Okay, so Möbius inversion. So suppose you have a poset and you have an integer valued function on that poset. Uh, then the Möbius inversion of m is another function, partial m, which satisfies the following. So for all a in your poset, if you want to compute m of a, then you can sum up the Möbius inversion partial m at all points above and including a, and then you'll recover m of a. So in this case, partial m is called the upper Möbius inversion, and so there's a dual. Maybe more commonly, you have the lower Möbius inversion as well, which is you can recover m by summing below. But we're going to look at the upper Möbius inversion. And another perspective on this, which we'll come back to later, is that there's really a function associated to each poset called a Möbius function. Um, and the Möbius function is it's really a function on the incidence algebra, so the set of all intervals of P. But you can think of it as a function defined on all pairs of elements of P. And if two elements are incomparable, you're just going to assign them 0. Um, you assign a comma a, you assign that value 1, and then if you want to assign, if you have an interval a less than b, then you assign that the number by looking at all c strictly between a and b, possibly including a. You look at the Möbius function that you already computed, sum those up, and you take a negative. Okay, so it's recursive. You start with a comma a's, and then you build up one step at a time from there. And so if you have that Möbius function, so that's a function that's associated to the poset, it's kind of intrinsic to the poset, then you can compute this Möbius inversion of any function by doing this sort of convolution. So you take m and you convolve it with this Möbius inversion function. You recover your, or sorry, you convolve it with the Möbius function and you recover the Möbius inversion of m. Okay. And so let's just do a quick
Alex, should we
example.
think of the poset as finite?
Yeah, so for this talk, we can just think of it as finite in general. So to make Möbius inversion work, you want to have a locally finite poset, which means that every interval, so if you have a less than b, there's only finitely many points between a and b. And that's just to make all these sums finite. Yeah. So here's an example of a poset for elements with these relations. And then I guess there's a implicit relation from a to d as well. And here's just an integer valued function on this poset. And here's its Möbius inversion. So if I want to compute any of the blue numbers, then what I should do is I stand at that point and I add up all the red numbers at and above that spot in the poset. So if I'm at A, then to get 2, I'm going to add up all of the red numbers at and above A. So I get 0 plus 1 plus 1 plus 0, and I get 2. And then same at B. So if I want to compute M, then I'm going to look at partial M at and above B. So I get 1 plus 0, I get 1. Same at C, 1 plus 0 is the blue one. And then at D, it's 0. And so that's how Möbius inversion works. So if I wanted to be, do this in a way where I didn't just kind of look at it and figure it out, then I would compute the Möbius function for this poset, and then I could recover partial m using that convolution formula. Okay. So we're going to kind of want to enrich this Möbius inversion story. So Möbius inversion only deals with integer valued functions on posets. What we want to do is actually look at algebraic structure on a poset. So we're going to say, we're going to have linear, or we're going to have vector spaces at each point on our poset, and then linear maps between those vector spaces. And so that's what's called a P module. So for us, a P module is just going to be a functor from the poset to the category of vector spaces, where you view the poset as a category. And really, that's doing exactly what we said. You're just assigning a vector space to each point of the poset, and then whenever you have a relation in your poset, then you get a linear map between those two vector spaces. And functoriality is just telling you that everything commutes. And so these things, these P modules form a category, vect P, and the morphisms between those are natural transformations. And the dimension function of a P module M, so it's just it's an integer valued function, dim sub M, which just assigns the dimension of the vector space at A to the point A. Okay, so here's two examples. So it's the same poset as before, and then I've attached a vector space to each point in the poset. And then between any two related points in the poset, we associate a linear map. So on the left here, with the vector space R2, two copies of R, and then the linear maps are projections. So project onto the X coordinate, project onto the Y coordinate. And then these maps into the zero vector space are just zero. And then essentially the same module on the right, except I've changed the map on the bottom. So now instead of having two projections, it's just project onto X in both directions. Okay. And both of these have a dimension function. Just take the dimension of each of those vector spaces. We get the blue function, which is exactly the same function we saw before. And so I can Möbius invert the dimension function, and we get the red numbers that we saw before. Okay, and sort of the idea now is, okay, we want to do Möbius inversion in a more sophisticated way. So in a way that doesn't just look at the numbers, the red and the blue numbers, but actually takes into account the algebraic structure. So takes into account the vector spaces and the maps. So we're going to do Möbius inversion in this more algebraic way. And it's going to generalize the Möbius inversion at the number, or at the level of numbers. So it's we're going to be able to recover the Möbius inversion of the dimension function from sort of this algebraic perspective. And so that's what we mean when we say categorify. Okay, so one of the pieces that we need is this enriched hom. So if you think about natural transformations between P modules, those themselves form a vector space. So I can take two natural transformations between P modules and add those together just by adding component-wise. I can scalar multiply just by multiplying each component by the same scalar. And so we get a vector space, which we'll call the enriched hom vector space. So let me give you an example. So here's a simple poset, 2 points with one relation. And on the right, each row is a different P module on that poset. So the top row is just a simple P module where you have one copy of R at the left point and then a copy of 0, and then the map has to be 0. N is just an arbitrary P module. We just have an arbitrary vector space, V and W, and then a linear map between them. And so we want to look at what are all the possible transformations between M and N. And so that's essentially saying, okay, what are all of the possible vertical maps so that this square commutes? And because this is the 0 vector space, the map on the right has to be 0. So really we're just saying, okay, what maps can you put here on the left so that this all commutes? And because, this top right path is 0, then this bottom left composition also has to be 0. And so what that's saying is that this vertical map on the left has to factor through the kernel of F. Okay. Or another way to say that is wherever this map on the left is completely determined by where I send 1. And so I have to send 1 to something in the kernel so that this composition is 0. So there's a 1-to-1 correspondence between natural transformations and the kernel of F. And so in this case, it's not just a 1-to-1 correspondence, it's actually an isomorphism of vector spaces. So our enriched hom vector space is actually isomorphic as a vector space to the kernel of F. Okay. So this enriched hom gives us a functor. So let's fix a p module M. And we'll look at the functor enriched hom from M into something. And so that takes in another p module N, and it spits out a vector space. Okay. And this functor is left exact, which means, so if we start with an exact sequence of p modules, A, B, and C of this form, and then I apply this enriched hom from M to that sequence, then I get an exact sequence, hom MA, MB, MC. And so that means that, we can do some homological algebra. So for each D, we can take the right derived functors of this enriched hom functor. And I'll kind of recap how we do that, the recipe for doing that. But we're going to call those functors the enriched X functors. Okay, so if you've seen this in homological algebra or even just algebra, you sort of classically you take these hom functors and you do this right derived construction, and those give you the X functors, which somehow measure the failure of exactness of this hom functor. So we're doing sort of exactly the same thing, except instead of just like an ordinary hom, we're using this enriched hom. Okay, and so the recipe for constructing X is the following. So what you do is you start with the module that you're sort of Xing into, so N in this case, and you construct what's called an injective resolution. So that's an exact sequence where you include into an injective object in your category, and then you continue that sequence as an exact sequence. So you compute some injective resolution. So I0, I1, I2 are all going to be P modules, but they're going to be these special injective P modules. And then you apply hom, your enriched hom from M, to that complex, or this exact sequence, and you get a chain complex. Okay, so because hom is not exact, this isn't necessarily going to be an exact sequence, but it will be a chain complex or a cochain complex. And so you can compute its homology at the D spot, and that's what you call the Dth X object. Okay, and this is going to be a vector space. And then, you can check that like this doesn't depend on the choice of injective resolution and so on. And that, in fact, in the category of P modules, we always have an injective resolution. So you can always construct this thing. This thing always exists. Okay. So what we're going to do is we're going to kind of do this Möbius inversion at this algebraic level. We're going to look at this this X functor for a specific class of modules, which are called the simple modules. So a simple module, we'll say R sub A, so fix some A in your poset. The simple module is defined just by putting a copy of R at that point A, and then putting zeros everywhere else, and then all the maps are just zero. So it's kind of like a skyscraper, just put a copy of R at whatever point A you want to consider. And so we can, we could take hom from that simple module into any other module, and then we can take those derived functors and we get X associated to that simple module. So let me give you an interpretation of what that's doing. So what are you doing when you kind of probe your module M with one of these simple modules? So what ends up happening is, so let's say you're mapping from a simple module at A, then you're standing at A, so that's M of A, and you're looking above A as well. So you look at all points P greater than A. That gives you kind of a submodule of everything above A. And you take a limit of those vector spaces. And so there's an induced map from M of A to everything above A. And that's this map here. And what hom does, this enriched hom does, is take the kernel of that map. So another way of saying this, more down-to-earth way of saying this, is that elements in this enriched hom, these are elements in M of A, so that when you map them any step upwards, you get 0. So in other words, if I have a point P, which is greater than A, and I'm standing at A, and I apply one of the maps from my P module from A to that P, then I have to get 0. So I think of these as the elements that died at A. So these are things that like exist at or before A potentially, but they don't exist at any place past A.
Alex, could you remind me the definition of the skyscraper module again?
Yeah. So that's just it's just put a copy of R at A and nowhere else. Yeah.
And then does that mean you're using vector spaces over R everywhere?
Yeah, these are all real vector spaces. Yeah,
Okay.
I could have chose a field if I wanted, but yeah.
Right. I'm with you.
Okay, so let me give you an example. So the example actually we did before. So in this case, we had a simple module. M was a simple module where like A is this left point, B maybe is this right point, and then we just have a copy of R at A and then 0 everywhere else. And when we took this enriched hom from M into N, then what we were really doing is we're saying, okay, look at N of A and then look at the map into everything above. Well, in this case, there's no limit to take. The only thing above is N of B, which is W. And so you're just looking at the kernel of this map from, N of A to everything above N of A, which is exactly the kernel of F. So this was just a special case of this more general thing. Okay. And so punchline is that the Möbius cohomology is exactly this derived functor. So fix an A, fix a dimension D. The dth Möbius cohomology of M at A is defined to be the dth ext functor from this simple module at A into M. Okay. So I'll come back to why that's useful. Let me maybe give you a more down-to-earth computational formula that doesn't, involve this these derived functors. So what you do is you can construct a resolution. There's one in particular, which is called the standard Coffrey resolution, and it involves taking chains in your poset. So I won't define this at the module level, but let me tell you what happens when you apply this hom-functor to these special P modules. So what you end up doing is if you're at the dth step in this injective resolution, then what you're doing is you're looking at chains that start at A of length D. And you evaluate each chain at the top element. So you look at the module evaluated at the top element of your chain, and you do that for all possible chains. You take a direct sum of those vector spaces. And so that's what we'll call the dth chain vector space. Okay. And then there's kind of natural maps that you get between these. So the maps go up in dimension, so you get a cochain complex. And Möbius cohomology then is exactly the homology of this cochain complex. So the idea again is just look at chains, evaluate at the top of the chain. That gives you, your dth chain vector space, and then you compute the homology of this cochain complex. So let's do an example real quick. So, okay, so on the left, I have one of my P modules from before, and we're going to compute the Möbius cohomology at each point in our poset. So let's look at A. So A was this bottom left point here. So what I'm going to do is I'm going to look at chains of length D starting at A. So chains of length 0 starting at A. There's only one chain of length 0 starting at A, and it's just A itself. And then you evaluate that chain at the top element, which is just A. So we get a copy of R2. So that's this copy of R2 right here. Okay, and then we look at chains of length 1. So we're going to look at chains of length 1 that start at A. So there's 3 of those. So there's the chain A to B. And you evaluate that chain at the top element. So you evaluate at B, you get a copy of R. There's a chain A to C. You evaluate that chain at C, you get a copy of R. So we got 2 copies of R. And then there's one more chain, which is A to D. You evaluate that at D, but you just get 0. So in the end, we just get 2 copies of R. And then the maps between these chains end up just being sort of take these two maps and squish them together. And so you get the identity matrix. And then we could go higher. So we can look at chains of length 2, but there's only one, or actually there's two of those. There's A, B, D, and A, C, D. But both of those evaluate to 0 at the top element, so there's nothing there to compute. So this is our cochain complex at A. But this is an isomorphism. It's just the identity. So when you take homology of this thing, you just get 0. Okay. So let's do the same thing at B, and then C will be symmetric. So at B, we're going to look at chains of length 0 starting at B. There's only one of them. It's just the point B, and you get a copy of R from that. And then we're going to look at chains of length 1 starting at B. So that's B to D. That evaluates to 0. So this is our cochain complex. When you take homology of that, it's just you get a copy of R in degree 0. And then same with C. And then with D, everything's trivial because we're just looking at chains starting at D. Everything's 0 above D. So we get 0. So that's our Möbius cohomology. Let's look at the other example, which is a little more interesting. So in this example, essentially everything's the same. So the whole chain computation to get the vector spaces in our chain complexes are the same. The only difference is that this map changed when we're computing Möbius cohomology at A. So now the map changed from the identity to this rank 1 matrix. And so when you compute, homology of this thing, so kernel mod image, you're going to get something one-dimensional in degree 1 and then one-dimensional in degree 0. And so it's sort of you split the cohomology, kind of you spread it out over cohomological dimensions, right? And then you still get the same cohomology at B and C. Okay. So why is this useful? Why does this categorify Möbius inversion? So the theorem, and so I'll credit this to Amit and Möbius Skraba. So they proved this with Möbius homology. And so essentially this is just the dual formulation of that theorem. So the theorem is that if you take the Euler characteristic of the Möbius cohomology of M at a specific point A, then you recover the Möbius inversion of the dimension function evaluated at A. Okay, so fix an A. Look at the Möbius cohomology of M at A in all degrees, take their dimension, and then take the alternating sum. Okay, so this thing on the left is the Euler characteristic of the Möbius cohomology. That should be equal to the dimension function Möbius inverted, and then evaluated at that point A. Okay, so let's look at this example again. So we already computed the Möbius cohomology. Okay, we got 0 and then R, 0. And so what this theorem is saying is that if I compute the Euler characteristic of these Möbius cohomologies, I should get the red numbers. So remember the blue numbers were the dimension function, and then the red numbers are the Möbius inversion of the dimension function. So, okay, Euler characteristic of 0 is 0. So that corresponds to the 0 at A. Euler characteristic of just one copy of R in degree 0 is 1. Same thing at C. So that gives me these 1s at B and C. And then Euler characteristic of 0 is 0. Okay. And then in our second example, remember the dimension functions and their Möbius inversion were the same between this example and the last example. So we should get the same numbers. The only difference is sort of we got that number by some cancellation at A. So at A, in this example, we sort of we got some non-trivial Möbius cohomology in degrees 0 and 1. But at the level of Euler characteristic, those cancel out. And so the Euler characteristic still gives us the Möbius inversion at A. Okay. So, that's maybe a good place to pause and just ask if there's any questions. Okay, great. Okay, so I want to kind of push this a little further. And the goal of what I'm going to talk about now is to categorify some other kind of combinatorial statements that are originally due to Rota. So we're going to introduce some operations on poset modules. So we're going to start with a monotone function between posets. Okay, so P and Q are posets, and then we have a monotone order preserving function. And now suppose you have a P module M, and then you have a Q module N. Do I have to revert? I don't know. So the push forward of M under F is going to be a Q module. So you push M to Q. And it's defined as follows. So if I want to evaluate F lower star of M at a point X in Q, I look at all points A in P that when you hit them with F, you get something bigger than X. Okay, so that gives you a submodule in P, kind of a subposet in P of all the things that are greater than or equal to X when you apply F. And then I take a limit of that diagram. Okay, it's kind of like taking the smallest element, but you might not have a smallest element, so you need to take a limit. And then there's another kind of a dual construction, a dual way of pushing forward, which is called push forward with open supports. And you do something dual, so you look at all points A and P that when you hit them with F, you get something less than or equal to X. And now you take a co-limit. And then the pullback is simpler. So you start with a module N Q, and you want to pull it back to a module on P. So you just pre-compose with F. So you just apply F, evaluate the Q module N, and then that gives you a P module, which is the pullback. So I guess in more fancy language, I think this is a right con extension. This is a left con extension, and then this is just pullback. Okay, and so these give us functors. So if we start with a monotone function F, then we're going to get two kind of push forward functors, which take P modules to Q modules. So this is like F dagger and F lower star. And then you also have a functor going backwards, which is F upper star. It pulls back from Q modules to P modules. Okay. And so Justin Curry, I think in his thesis, observed that there's adjunctions between these functors. So this F dagger, this push forward with open supports, is left adjoint to the pullback. And the pullback is left adjoint to the push forward. Okay, so we have this diagram of adjunctions here. And what that means in categorical language is that you have isomorphisms of these hom sets, but the hom sets between P modules are just natural transformations. Okay, so our goal is going to be to enrich this. So natural transformations, we said, are actually vector spaces. We can think of them as vector spaces. And so we want to see if these isomorphisms, which are just bijections right now, can actually be upgraded to isomorphisms of vector spaces. Okay. We'll come back to that though. So let me talk about Galois connections. So a Galois connection is a pair of monotone functions between posets. So you have F going from P to Q, G going from Q to P. And it's a Galois connection if the following holds. So for every A and P and X and Q, F of A is less than or equal to X if and only if A is less than or equal to G. And we'll denote it by like F turnstile G. And that's because these really are just adjoint functors in a certain sense. So if you treat P and Q as categories, like we have been, and then monotone functions are just functors between those categories. And then a Galois connection is exactly saying that you have an adjoint pair of functors between those two categories. Okay. So a really simple observation, but kind of deceptively simple, because it turns out to be really nice, is that if you have a Galois connection, then there's relationships between sort of those push forwards and pullbacks that we talked about. So it turns out that the pullback of G in a Galois connection is the same as the push forward of F with open supports. And the push forward of G is the same as the pullback of F. Okay, so maybe it's easiest to look at this diagram. So like, F goes this way, G goes this way. So I can push forward along, a P module along F, and I get a Q module. So that's F, dagger. Or I can start with a P module, the same P module, but I can pull it back along G, and I still get a Q module. So I'm saying if I push forward with open supports, or if I pull back with G, that gives me the same functor. So that's this top thing. And then there's another statement, which is if I have a Q module, I can push that forward under G, or I can pull that back under F, and those give me the same thing. So that's this middle arrow here. And then there's no analog that I know of for F push forward. But so if I just combine that with Justin Curry's theorem, that tells me that pullback along G is left adjoint to pullback along F. And then push forward along G is left adjoint to push forward along F. Okay. And so we have these natural isomorphisms. Pull back along G, isomorphic to, or left adjoint to pull back along F. Okay. Same for push forward. So it's kind of reverses sort of the direction, right? So F is left adjoint to G, but then when you do these pullbacks and push forwards, you reverse the adjunction.
Alex, can I ask a quick question?
Yeah.
So like, if you were defining a homotopy equivalence between spaces, the two maps are like sort of interchangeable in some sense, right? But here F and G are not really interchangeable because one's like the left adjoint and one's the right adjoint. So that's why the dagger, like this open support one, only appears on F and never on G in any of these.
That's right.
Is that right?
Yeah. Yeah, there's some directionality to this. Yeah.
Yeah.
Okay. And let me give you a simple example. So P is going to be the set of, I guess, non-negative even integers, and then Q is just going to be all integers. And then F is going to be inclusion of evens into all integers, and then G is going to be essentially just round down to the nearest even integer. So like 2 or 3 would get mapped to 2, 2 would stay at 2, etc. So you can check that this is a Galois connection, kind of a classical example, is rounding down. And then here I've put a module M on P, so just on the even integers, and I just put 0 and then 1 copy of R, 2 copies of R, and so on. I didn't say what the maps are. It doesn't really matter for this example, but they could just be inclusion. And so, okay, let's say I want to push that module forward from P to Q. That's sort of extending from the evens to all of the integers. So the push forward with open supports, you're saying, okay, look at let's say I'm standing at 1. I look at everything less than 1, every even integer less than 1, and I take a co-limit. So essentially that says look at everything less than 1 and sort of take the vector space kind of at the end of those points. So I'm just going to associate 0. So at 3, I'm going to say, okay, look at all the even integers less than 3. So that's 0 and 2. And I'm going to take a co-limit of that subdiagram. But that's just saying, okay, look at the rightmost point in that subdiagram. So that's R1. So we're just going to get a copy of R1 there. Same thing at 5. Look at everything, every even integer less than 5. And I take the largest one. That's going to be the limit. So that gives us an R2 and so on. So you're kind of, you're looking left. So this is the left con extension. But that really is exactly the same as rounding down and then evaluating at M at the rounded down point. So like if I'm at 5, I'm going to round down, which means apply G and then evaluate at 4. Right. So this really is this push forward with open supports is really the same as rounding down and then evaluating. Okay. And then push forward of M, that's sort of rounding up, I guess, but there's no analog in terms of G. It's just it's a right con extension. So
minor clarification. So this function for rounding down to the nearest even, wouldn't that be n maps
it
to
should be
twice?
2. Yeah, that's right. Yeah, that's a typo. Thank you. Okay. So what is Rota's Galois connection theorem? So this goes back to Rota, who, introduced all of this like Möbius inversion on general posets. So Rota's Galois connection theorem says if you have one of these Galois connections, then the following identity holds. So if you have any A, P, X, and Q, what I can do is, so, A is fixed, and I just look at all of the points P in the poset P that map to X in Q under this map F. And I just add up their Möbius functions from A to P. Okay, so for all those points P in the preimage of X. So mu sub P here is the Möbius function associated to P. I can do the same thing on the other hand. I can fix X, and I can look at all those Q's in big Q that map to A under G. And I can add up all those Möbius functions. And those two things should give us the same thing. Okay. So a nice identity, but maybe a little opaque. So let me give you a nice reformulation, which is an observation of Aziz Gulen and Alex McCleary. So if you have a Galois connection, and let's say you have a integer valued function on n, then there's two functions you can define on P. So on one hand, you could pull back n under F, which is just precomposed with F, or you can push forward n under G. So G goes from Q to P, so we could push forward n. And what you do is kind of similar to how we were doing push forwards with for P modules. You just look at all of the points X and Q that map to A under G, and you add up their values under n. So in this reformulation of Rota's Galois connection theorem, which is equivalent to Rota's original formulation, the statement is that for any integer valued function on Q, I can either pull back n to P and then Möbius invert in P. So that's what this is saying. It's saying pull back n to P, Möbius invert there. Or I can first Möbius invert n in Q, and then I can push it forward under G. And those two things should give us the same thing. And that's completely equivalent to the formulation involving the Möbius functions that I showed you before. So this is the statement that we're going to try to categorify. Okay. And here's that statement, which maybe doesn't look like it relates at all, but the statement is that those isomorphisms, so those adjunctions that we had before, so G, the pullback of G is left adjoint to the pullback of F, and the push forward of G is left adjoint to the push forward of F. Those actually can be upgraded to isomorphisms of vector spaces. So these enriched hom vector spaces that we introduced earlier. And this is what we're calling sort of the categorical Rota's Galois connection theorem. So maybe this one on the left specifically. So I claim that this contains, as a special case, this statement here. Okay. And so let me try to explain why this is an actual proper generalization and categorification. So we're going to decategorify. So let's look at this formula with the pullbacks, and let's take a specific example, or plug in something specific for M. So let's just plug in the simple module at A. Okay, so I get this this adjunction here, and let's look at the right hand side. So let's focus on that. I can take derived functors on both sides. So I get X, on the left, and I get X on the right. The X on the right is exactly what we defined to be Möbius cohomology. This was that thing where you prod a module by prodding with simple modules, and then you take derived functors, and that's what we called the Möbius cohomology in this case of the pullback of n. Okay, and now what happens if I take Euler characteristics? Well, one of our theorems was that the Euler characteristic of Möbius cohomology should be the Möbius inversion of the dimension function. So if I take Euler characteristic on the right here, I get the Möbius inversion of the dimension function of the pullback. Okay, and then it turns out the dimension function of the pullback is the same as just taking like the pullback of the dimension function. So on the right, we get, yeah, the Möbius inversion of the pullback of n. On the left, there you need to do a little bit more combinatorics and kind of shuffle some sums, but it turns out that's the same as doing first Möbius inverting n and then pushing forward under G. And this is exactly the formulation, Alex and Aziz's formulation of Rota's Galois connection theorem. And I guess the last step is that, okay, so we should say you can do this for any integer valued function n. So then the last piece is to realize that, for any integer, little integer valued function little n, there's a big N that has that function as a dimension function, right? And so you recover that statement. But it also shows that sort of this is a much stronger statement because the Möbius functions and Rota's Galois connection theorem only operate at the level of like integer valued functions, whereas this adjunction is saying something a lot stronger. It's it's incorporating all the algebraic information in the module. So decategorifying gets us the Rota's Galois connection theorem, but if we don't decategorify, we actually contain a lot of information here that we lose if we pass to the dimension functions. Okay, so that's that. And so the last thing I want to talk about is just towards some open questions. So back when I defined the Ext functors using like injective resolutions, there was actually something that we talked about called the standard Coffrey resolution, which I didn't define. But I want to talk about Coffrey modules real quick because these are kind of the building blocks of Möbius cohomology. So if you fix a vector space V and then you fix some A in your poset, you can define a P module, V down arrow A. And what you do is you just put a copy of V, at every point below A. So basically you take a principal down set at A, just look at all the points below A, you put a copy of V, and then all of the maps are identity maps, and then zeros everywhere else. And so these are called elementary co-free P modules. Okay, a free module would be kind of the dual where you take upsets, so that's why they're called co-free. And then, so those are elementary, and then a co-free module is just saying take a direct sum of these elementary ones. Okay, so at each point A, you might take a different vector space and you put a copy of that vector space at every point below A, but then at B, you might take a different vector space, V sub B, take a direct sum of all those modules. Those are called co-free modules. And every co-free module is an injective module in the category of P modules. And so that's why it's part of the reason we were able to use them to construct kind of our derived functors. Not only that, they're also acyclic, meaning their Möbius cohomology is trivial. It's all concentrated in degree 0. And that's sort of a consequence of the fact that we were able to use them to define the Möbius cohomology. Okay, so here's our examples from before. So that module, that first one we defined where you project onto X, project onto Y, that's actually co-free. So it's a direct sum of sort of this principal or elementary free or co-free module and then this elementary co-free module. This bottom one is not co-free. It doesn't split this way. And so so we have a conjecture related to these co-free modules. So the conjecture is that a P module is co-free if and only if the Möbius cohomology at every point A is trivial in the sense that it's concentrated in degree 0. So it's 0 for all degrees above 0. Possibly you can have something non-zero in degree 0. Okay, so one direction's easy. So the first direction going forward, so if our module is co-free, then it's injective. Injective things in a category are always acyclic. They always have trivial cohomology because you can use them to construct injective resolutions, but then if you're injective, then you get an injective resolution of length 1. And then when you take homology of that, you get something trivial. So it's the reverse direction that's non-trivial. potentially. So if something has all trivial Möbius cohomology, does that mean it's co-free? So the motto that I want to be true for Möbius cohomology is that it gives a measure of how close a P module is to being co-free. So if this conjecture is true, that's kind of how I think of Möbius cohomology. I guess it's still kind of how I think of Möbius cohomology, but the conjecture would make this a stronger statement. And then a corollary to that would be that co-free P modules are the same as injective modules. And again, one direction we already have, co-free implies injective. The converse would follow from the conjecture. So if you had something injective, then you know that it's acyclic. It has no non-trivial cohomology. So if the conjecture is true, that means it has to be co-free. So, you know, so maybe, you know, if somebody watching this has some idea, some representation theorist or something, you know, this is just saying co-free is the same as injective, is the same as acyclic. So we have some evidence that this is true, and there might be a simple counterexample as well, but hopefully maybe somebody has some ideas on that. So let me show you how this appeared in our example before. So we had these two modules. The co-free one was this one here, where the Möbius cohomology at A kind of was 0. In the second example, we had something non-co-free, and that kind of manifested when we had non-trivial Möbius cohomology. Okay. And so that's it. So thank you.
Thank you so much. So
Yeah.
before we get to questions, I would ask everyone to unmute themselves so that we give a round of applause for the speaker.
Thank you.
And
Thank you.
Now it's time for questions. Feel free to ask or raise your hand, and I'll.
I just have a question. Do you have a feeling for, is the conjecture true for finite posets? Do you think that that makes a difference?
So I don't think that makes a difference. I think it's true for locally finite posets in general.
Okay.
Or that would be my conjecture, yeah.
More questions?
So Alex, I take it that the injectives in this category of P modules aren't like classified in any sense.
I guess this would be the classification. Yeah. So I think they're just co-free things. So they're just direct sums of downsets, or like elementary downsets. Yeah.
Your P modules are just like functors from the post set to vector spaces.
That's right. Yeah.
Yeah.
So I mean, yeah. So it's a little easier here because we're working with vector spaces. I mean, in sort of the paper that we posted, we work over a general abelian category. So then it's more complicated because now you can't just take like general downsets. You have to take like downsets where the constant module or like the constant object on those downsets is an injective thing in that category. But in vector spaces, everything's injective, so we don't have to worry about that. So I guess there's a more general conjecture, which is like I would say the acyclic things are exactly like the co-free things, where like on every downset you have an injective object in your whatever category you're working in.
More questions?
I'll ask one more. So representations over a quiver are more general than representations over a post set, right? Like you might have two directed arrows between two objects.
Yeah, that's right. Where like
have
you don't
all thought about
enforce
those at all?
No, not in this context. Yeah, that'd be like, forget the commutativity relations in your post set, right? You're kind of saying. So like you can do all this in that context. Like yeah, I guess that's interesting. So you can do this Möbius cohomology, that still works. what maybe doesn't work or like is less interpretable is what is the decategorification? Because now you're trying to say like you're trying to look at the Möbius function of a quiver, which I don't think maybe isn't well defined. Yeah, so I guess it'd be interesting to just kind of naively decategorify and just like try to interpret that or see if it makes sense at all.
Thanks.
Okay, do we have further questions? So if not, then thanks again so much. I will stop the recording here, and then we can have more questions afterwards.
All right, thank you.